This section is gears, pulley drives, and sprockets. So gears, pulleys, and sprockets. These three powertrain elements transfer energy through rotary motion. So you can have different gear sizes, pulley sizes, sprocket sizes to change the speed of motion, direction of rotation, change the amount of torque available to do work. So that's the big thing. So the more torque, the more power you have to spin. Right. Gears. A gear train is a mechanism used for transferring rotary motion and torque through interlocking teeth. Gear train is made when two or more gears are meshed together. Driver gear causes the motion. Motion is transferred to the driven gear. That makes sense to everybody? Kind of important. Mating gears always turn in opposite directions. So this blue gear, if you turn it that way, the red gear is going to turn that way, and this blue gear is going to turn that way. So as you go through like down a train like that, you're going to switch directions each way. An idle gear allows the driver and the driven gears to rotate in the same direction. So this red one would be an idle gear. And mating gears, like the two gears that are stuck together, always have to have the same size teeth, otherwise it won't work very well. So RPM, so revolutions per minute, of the larger gear is always smaller than that of a slower gear. So a smaller gear will turn more times in the same amount of time than the larger gear it's meshed to. Does that make sense to everybody? So when you're slowing down the gear, that means you're kind of adding more torque. So you could lift more with, if you went from a small gear to a large gear, you could lift more than just the small, like if you just had the small gear by itself. Does that kind of make sense? If you go from a big gear to a small gear, you're going to speed it up, but it's going to have less power. So if you like drive a big gear and have that gear turn a small gear, the small gear is going to turn faster, but you're going to have less power on it. Does that kind of make sense? Alright, so I'm just going to go through that again. So N is the number of teeth, D is the diameter, the goofy looking Greek symbol is the angular velocity or speed. That's how fast it turns in revolutions per minute. T is torque, that's how much turning force it has. You can think of it like that. These are our equations for gear ratio. So gear ratio is either the number of teeth in the gear that's going out over the number of teeth in the gear that's going in. The diameter of the output gear over the diameter of the input gear. The angular velocity of the input gear over the angular velocity of the output gear, or torque out over torque in. So you want to notice that it's always out over in except for angular velocity. So make sure you notice that one is going to be different. Does that kind of make sense to everybody? What is the gear ratio between A and B? So if A is our input gear, and so if it's going kind of this, whoops, if it's going this way, from like input to output, A has 20 teeth, B has 12 teeth, so the gear ratio would be 0.6. That makes sense to everybody? The next one, we go from B to C, 5 over 12 is 0.42, and from C to D, now we've got a bigger output gear than input gear, so it's going to be 4 over 1, or 20 over 5, so 4. Any questions on how to find the gear ratio of things? Right. So if we figure out the total gear ratio, we multiply all these together. So the gear ratio between A and B, B and C, and C and D. We multiply those all together, we get 1 for the gear ratio. What would the gear ratio between A and D be, just by themselves? 1. 20 over 20 over 1. So what really matters is, for like a long gear train like this, is the first gear and the last gear. The idle gears in the middle here don't matter. That's why they're called idle gears. All they're there for usually is to change the direction of a gear. So you'll almost never see anybody put 4 gears in a row like this in an actual design, because that won't do any good. You might see somebody put a small gear in between 2 big gears if they want the 2 big gears to rotate in the same direction, or vice versa. Does that kind of make sense, what you'd put like 3 gears in a row for? Alright, and if the last one had 40 teeth, we do 40 teeth out over 20 teeth in, and the gear ratio would be 2. And if you added it all up the same way, you'd still get 2 if you did each individual set. Gear ratios for compound machines, they're going to be used similarly to mechanical advantage. So instead of, usually had like force out equals mechanical advantage times force in, either IMA or AMA, if you rearrange that equation. Torque's going to be the same way. So gear ratio and torque are, so torque is the equivalent to force, and gear ratio is equivalent to mechanical advantage. And to find the total gear ratio, do it the same way. You multiply all of the individual gear ratios together. Does it kind of make sense? It's a little complicated here. We've got a couple different things going on. We have a wheel and axle for this one, another little wheel and axle down here, and then a gear ratio. Does it kind of make sense to everybody? So you have to kind of go through each of those things individually in this kind of compound machine thing here. It's just a wheel and axle. So our mechanical advantage is going to be the effort distance over the resistance distance. So what's our effort distance here? If we're applying the force out here, our effort distance is going to be the distance from there to there, so 4 inches. And our resistance distance, what do you think that's going to be? It's going to be 1.5, which is the radius of the gear, because the output force is going to be applied to this other gear right there. Does that kind of make sense? Alright, so our first mechanical advantage of that first machine is 2.67, 4 inches or 1.5 inches. Any questions on any part of this? Alright. Next we're going to find our gear ratio. And the gear ratio, it's important to remember, does not actually affect the mechanical advantage at all. So this time we're just going to have number of teeth out over number of teeth in. We've got 24 teeth for that blue gear, so that's the output gear. 60 teeth for the pink gear is the input gear, so 24 over 60 is 0.4 for our gear ratio. Everybody understand how we got that? This part, we have our last mechanical advantage here. So this time the effort force, this is one part that can get a little bit confusing. Since this gear, the blue gear, is being turned, it is going to be our, its radius is going to be our effort force distance, and the resistance force is going to be the length of the arm for that distance. So we end up with 0.6 inches is the radius of the blue gear, divided by 4 inches is the length of the arm, and we get our mechanical advantage is 0.15. Any questions on that? So last thing we do is multiply the two mechanical advantages together to find the total mechanical advantage of the compound machine. So it's 2.67 times 1.5, and our mechanical advantage is going to be 4. So, and the gear ratio is just 0.4, and that's just the ratio of those two gears. Train, if we had the actual thing, these are supposed to all come together like in a cool machine that spins, but on this they won't. So what it's supposed to look like is you have a gear, you have like a gear here, and another gear here, and another gear on the same axle. Does that make sense? And then this other gear is meshed with that gear. And that'll be a better picture on the next slide. But so the two middle gears share a common axle, and that means you have a compound gear train. So that's how you can make like multiple gears to keep getting a bigger and bigger gear ratio, or a smaller and smaller gear ratio. So what we do here is we figure out the A is our driver, so we're going to go from A to B, and then from B to or C to D to find our total gear ratio. So to find the gear ratio between A and B, it's out over in, so it's 40 over 10. So the gear ratio there is 4. Between C and D, it's 50 over 20, so it's 2.5. So the gear ratio of that whole thing would be 10. Do you guys feel like you could build a device that had a gear ratio like that if you wanted to? And this is going the way it is here. The driver over here is going to slow it down. So it's going to be a slower turning thing. D is going to turn slower than A, but it's going to have a lot more torque. So a lot more like power to do things. If you went the opposite direction, A would turn much faster than D. So if you wanted to speed something up, you'd go the opposite direction. and then A would have a lot more speed but less torque. Pulleys and belt systems. Pulleys work essentially the same way as gears, except we don't have the number of teeth. So the equations are the same for like their ratios here, but you don't have number of teeth in that equation. And again, so if you turn this one at 30, this one's going to go slower. Last one we'll talk about is sprocket and chains. Again, these are the exact same as gears, except they just have a chain connecting them, and they work the exact same way. So again, faster at the smaller gear, slower at the larger gear, sprocket, I guess, in this case. Last slide, some advantages of pulleys and sprockets. So pulley is a belt, sprocket uses a chain. Pulley advantages are quiet, there's no lubrication needed, and it's cheap. Sprockets, the advantage is it doesn't slip, and it can apply ultimately a greater force than the pulley can. Big disadvantage of the pulley is it can slip. Disadvantage of the sprocket is higher cost, needs lubrication, and is noisy. Alright, you guys have any questions over any of this?